connected because I'm emotionally connected because the right hand side of your screen you see this the picture where I'm sitting. He's the residence of the Srinivasa Ramanujan. It's a residence in Kumbakonam. And the place this year I had not visited because of this pandemic situation, quite unfortunate. The place I visit every year because that is also my hometown. And this is the place where you have his residence. This is maintained by, it's basically taken care by the Shastra University and the group of researchers belonging to that, which involves Professor Bruce Byrne, Professor Andrews, and all these persons who are taking care of this information. So the Shastra deemed university is adopted this house where Ramanujan lived. And so this year, 1920, in which Ramanujan left us, and it's 100 years now. So it's I'm taking this time to speak on a particular topic, and this is related to the orthogonal polynomials and on the unit circle. And I'll speak something about some chain sequences and some concept of complementary chain sequences which we have introduced, and a particular illustration related to the Gaussian hypergeometric case. So when we speak about orthogonal polynomials, basically orthogonal polynomials, we all know that are defined on the interval or on the real line, and there are quite famous well-known polynomials like the Legendre and Chebyshev polynomials, which are particular cases of the Jacobi polynomial, and the other classical polynomials include the Logger and the Hermite polynomial. But what I'm interested in speaking is the Jacob polynomial, which Jacob introduced and studied extensively. And this is the complex polynomial on the unit circle, and which has all the inside and on the unit circle, and which has all zeros inside the unit disk, and something on the unit circle and something on the unit disk. And basically, this year 1920 has another connection with this. That is the year in which the book of orthogonal polynomial by Gaber-Szegő was published, and which paved a big line for working on orthogonal polynomials and special functions. So I would like to speak about these orthogonal polynomials. So basically, these phi-n's are basically the orthogonal polynomials, which are given by this relation with respect to the measure function mu, and the chi-n's are basically the corresponding parameters, which are given by these representations. So, and these polynomials always satisfy certain difference equations. These difference equations are basically involving these phi-n's and their reciprocal polynomials phi-n star. By reciprocal polynomial, by what this we do is we replace z by 1 over z conjugate and take the conjugate of the whole thing, or basically what we do is we simply reverse the coefficients, so we get the reciprocal polynomials. And these polynomials are related with reference to something called Schur parameters. These Schur parameters are basically nothing but the position of the polynomials at origin. And of course, they are closely related to another thing called Verbaliski coefficients. When we speak in the complex sense, that they are going to be the negative of them are going basically called as the Verbaliski coefficients. And basically, the Verbaliski coefficients or the reflection coefficients are mainly highly studied in today's context in quantum mechanics and several other studies. In our work also, we are interested in speaking something with the Verbaliski coefficients as well. So, and these Jacob polynomials, phi-n's, satisfy a three-term reconciliation, because we know that basically given any orthogonal polynomial satisfy a three-term reconciliation, and because there's basically they are in the Hilbert space, and with the continuous three terms that are satisfied by this because of this inner product behavior, we'll be able to see that. And in fact, there is a famous theorem called the Theorem of Forwards, which the Forwards theorem basically guarantees that. The Forwards theorem guarantees that every polynomial that satisfies this three-term reconciliation also gives back to the orthogonal polynomial with reference to a particular measure. And of course, similar to the Forwards theorem for the real line, we have the Wovenski theorem for the unit circle or the complex situation, where we say that given an arbitrary sequence of complex numbers alpha n, of course, these alpha n's turns out to be the Verbaliski coefficients, and then we can always find a non-trivial probability measure mu on the unit circle. With respect to this measure, we'll be able to construct the sequence of orthogonal polynomials using this particular three-term reconciliation. So what we have is either we have a sequence of orthogonal polynomials on the unit circle, or we have a sequence of complex numbers. Once we have a sequence of complex numbers, using the three-term reconciliation, we can get back to the orthogonal polynomial. So the three-term reconciliations and the orthogonal polynomials are basically the orthogonality property or equivalent relations, basically. So now, given these orthogonal polynomials, initially Jones, Thron, and Nastad, they worked something, and later much more characterization was given by Delsarte and Guinin. So I use it as a Delsarte Guinin. They've considered the following parameterization. So they consider this particular relation here, and by this relation, they gave two sets of polynomials, R1, Rn1 and Rn2. These two are para-orthogonal polynomials. By para-orthogonal polynomials, we mean that the zeros basically lie only on the unit circle. Zeros only on the unit circle. And they are not going to lie inside the unit disk. So once they are going to be only on the unit circle, these para-orthogonal polynomials are highly useful in studying the quadrature formulas. So they are basically called Delsarte-Guinin first para-orthogonal polynomials, or Delsarte-Guinin second para-orthogonal polynomial. So these are basically singular predictor polynomials. So they are in fact studied by Jones and Thron in their beginning work, and later Delsarte gave a much more clear characterization of it. And of course, this among these two, I'm much interested in the DG1 para-orthogonal polynomial, because these DG1 para-orthogonal polynomials satisfy a particular three-term reconciliation. And I said before, a polynomial satisfying a three-term reconciliation from which we'll be able to get back to the orthogonal polynomial, or we can get back to the para-orthogonal polynomial. So the three-term reconciliation is very important. And this three-term reconciliation satisfies something called the chain sequences. They have some coefficient conditions, and these coefficient conditions are called chain sequences. I'll tell you what a chain sequence in the coming slides. And these chain sequences are related to the Verbaliski coefficients here by this relation. So there is a relation between the chain sequences and the Verbaliski coefficients. So this is always there. So basically, what we are interested is so we know that the Forwards theorem or the Verbaliski theorem says that given this alpha n's, we'll be able to get the corresponding orthogonal polynomial. So now if we know the chain sequence, from the chain sequence, we'll be able to get the Verbaliski coefficients, and we can get the polynomial as well. So these are all the information we have. And if you want to study, know much more information about this first para-orthogonal polynomial, we have that work myself with Sriranga and Cleonice. We have done this work, and we have studied an extensive study of this work with all the zeros and the several other properties and the behavior of the measures. And of course, I'll go to the chain sequences. So I said there is a relation between the Verbaliski coefficients and chain sequences. So the recurrence relation for the R1 polynomial, or this basically we call it as a para-orthogonal polynomial of first kind, has a relation between the chain sequences and the Verbaliski coefficients. And we know that the Verbaliski coefficients give rise to the information given by these orthogonal polynomials, or the orthogonal polynomials on the unit circle. So what we can do is, if at all we study the chain sequence, we'll be able to get information about the orthogonal polynomials as well. That's the idea. So we'll just speak about what a chain sequence is. So a sequence Dn is called a positive chain sequence. If there exists another sequence Gn, of course, the G sequence is quite known in the history of continued fractions. And of course, you can see either the book of Chihara on the introduction of orthogonal polynomials, where he speaks about the chain sequence, or you can see the monograph of H.S. Wall on the analytic theory of continued fractions, where you can get this information about the chain sequences. So a sequence Dn is a chain sequence. If there exists another sequence Gn, such that the G0 takes the value between 0 and 1, 0 included, all other Gns takes the value between 0 and 1, such that the Dns are these particular positive chain sequences Dn are obtained from this relation, dn is related to 1 minus gn minus 1 times gn. And these gns are called basically the parameter sequences. And of course, when we wrote g naught is less than or equal to 0 or greater than or equal to 0, this equality condition precisely makes us one information that if g naught is 0, these gns become minimal parameter sequence, and this minimal parameter sequence gives rise the corresponding positive chain sequence, which we call as mn. So these mn's are very important. And now, once we have a minimal parameter sequence, we may have a maximal parameter sequence also. So for all these gns, we'll take the infimum of these gns, which we call it as the maximal parameter sequence. And H.S. Wall has given a nice characterization for this maximal parameter sequence by this particular relation. So this relation is very important in speaking about the maximal parameter sequence. So every polynomial may have a minimal parameter sequence and will have a maximal parameter sequence. Sometimes definitely we feel that the minimal parameter sequence and the maximal parameter sequence are two different sequences. So the entire polynomial sequence lies between these two things. So here further information is, if dn is a chain sequence with a parameter sequence gn, then dn plus 1 is also a chain sequence with the parameter sequence starting from gn plus 1. But once you start with gn plus 1, you are going to start with g1. So if dn plus 1, definitely will have a different minimal parameter sequence. And if it's minimal parameter sequence, if you call it as a script mn, then the script mn will be definitely less than the original mn plus 1. But the maximal parameter sequence will be the same. Only the minimal parameter sequence, if we replace the dn by dn plus 1, the minimal parameter sequence will have a change. So, of course, why we need to go for dn plus 1? Because we take dn plus 1 and consider the chain sequence from that. And from there, if we construct the corresponding orthogonal polynomial, we are going to get a new positive measure, which is mu hat. And this mu hat is going to give us new set of polynomials. Of course, the main important thing in information here is dn plus 1 is also a positive chain sequence whenever dn is a positive chain sequence, but the converse is not true, because if dn plus 1 is a positive chain sequence, you cannot go to the dn. So these are some restrictions available here. With these restrictions, we can study. So these modified parameters will give us a new given by this relation, where the Verbaliski coefficients alpha n's are given in terms of these chain sequences. They are basically given by corresponding chain sequences. So these mn's are very important. These mn's are very important. And one more information about these mn's is required, which we'll do a bit later. So once we have these mn's, what I was interested, what my research group was interested was to consider about the behavior of mn's. And we can see that these Verbaliski coefficients are related to these mn's by some particular relation. And the cn's are any complex numbers. We are going to give this. So the Verbaliski coefficients depend uniquely on these mn's. And of course, we feel that whenever we have a perturbation in the minimal parameters mn, then there will be a difference. There will be a difference in the Verbaliski coefficient. So there will be a perturbation, and automatically there will be a change in the given polynomial. It is, we took a polynomial, we want to find the Verbaliski coefficient, from which we want to find the minimal parameter, and then from the minimal parameter sequence, we want to make a disturbance, see what is going to happen to the Verbaliski coefficient, and retrace the polynomial and see the relation between the original polynomial and the resultant polynomial. So the Verbaliski theorem, which guarantees this procedure, because Verbaliski theorem guarantees that whenever we have a Verbaliski coefficient, we'll be able to get the orthogonal polynomial. Right. So based on this, we gave a definition. The definition was not so great, but still the definition had a remarkable improvement. So what we did is, instead of the original sequence mn's, we have considered a new one, which we call as kn's, which is 1 minus mn. Instead of mn, we have taken 1 minus mn. We took that as a positive chain sequence. And from the chain sequence, we are trying to construct all the information. This is what we were interested. And we called this as complementary chain sequence because the mn's lies between 0 and 1. So once mn's lies between 0 and 1, our kn's also going to lie between 0 and 1. So we call this as a complementary chain sequence, not just because it is 1 minus. There are some other reasons as well, which we'll just provide shortly. Of course, one important information we were able to get is, we have these 1 minus mn's, which are giving us kn's. So let us take dn as a main chain sequence. which is having Mn as its minimal parameter sequence. Then we considered Kn, which is another chain sequence, from which we are going to get alpha n as the required sequence. So the Dn is a chain sequence, alpha n is another chain sequence. So Dn, this will give rise to Mn's. From Mn's, we will get 1 minus Mn, which we call as kappa n. From this kappa n, we are getting alpha n's. So we want to find the relation between, maybe I don't want to call alpha in ANs. So we want to find the relation between these ANs and these things. We are interested in this information. How to find the relation? That was basically the story we had here. So, of course, there is an important property here. If DNs and ANs are two complementary chain sequences of each other, then they both are called SPPCS, if and only if they satisfy this relation. This information came from the maximal parameter chain sequence, and I call this as a relation because of this information. This lemma is very useful while considering the chain sequence and its complementary chain sequence without using any information about the minimal parameter sequence. So once you know the DN sequences, then you can get the AN sequences and you'll be able to speak about the property called SPPCS, which is this information. What SPPCS is? SPPCS is nothing but single parameter positive chain sequence. Means that the minimal parameter and the maximal parameter both are becoming same. Because we know that every positive chain sequence will have a minimal parameter chain sequence and a maximal parameter chain sequence. If we bring the minimal parameter and maximal parameter as equal, then the positive chain sequence will become unique. Because between minimal and maximal parameter, there will be so many parameter sequences, so many chain sequences. If you bring both of them together, we'll have only one chain sequence that will be unique. So in fact, so we go back to our previous result, which guarantees that these DNs and ANs, once we are given a sequence DN, then the complementary chain sequence gives AN. This DN and AN becomes a single parameter positive chain sequence if and only if they satisfy this property. And of course, here I've written only DN. I will tell you why I've written only this as DN, because we know that the pictorial notation is we have M0 as the minimal parameter sequence, capital M0 is the maximal parameter chain sequence. So we have got two sequences of chain sequences, and we can see here, we can bring them together. There will be a lot of chain sequences lying between them. So once we try to bring them together, the number of chain sequences between them will become less. And at one stage, when they are going to be equal, there will be no other chain sequence, and that will be the unique chain sequence which will have. This is going to have a unique chain sequence. It will have a unique chain sequence in your situation. Of course, one of the important things is, I said DN is going to be the single parameter chain sequence. If DN is not a single parameter chain sequence, single parameter positive chain sequence, then AN will be the single parameter positive chain sequence. Of course, there is no big mathematics on this, because if DN is not a single parameter main sequence, then its minimal parameter and maximal parameter will satisfy the property that this value is not equal to infinity, less than infinity. Because already long back I told that Wall has given a criteria that the value is equal to infinity. So this value is, because it is not SPPCS, so once it is not a single parameter chain sequence, then the value is less than infinity, not equal to infinity. So it is going to converge. So once it is going to converge, the nth term will become 0. So once the nth term will become 0, I can replace, once it is going to become 0, the reciprocal of it, replacing mj by 1 minus kj, I can see that the reciprocal goes to infinity. Precisely this gives us the maximum parameter sequence, or it is going to give us the information that the minimal and maximum parameter sequence satisfies the same property. So it is a single parameter positive chain sequence. So if DN is not a single parameter positive chain sequence, then AN is. So automatically, if AN is not a single parameter chain sequence, then DN will be a single parameter chain sequence. Right? So in fact, precisely for all values of Mn between 0 and half, AN, the complementary chain sequence, gives a single parameter positive chain sequence. Between half and 1, the original chain sequence will give us the single parameter chain sequence. This is what we have the information here. Right? Of course, the proof is quite simple, which follows from Wall's criteria. I'm just skipping it and going further. Of course, there is another nice relation between this, these two chain sequences. If you write the corresponding G sequence, the G sequence satisfies this nice relation between them. The convoluted fraction type relation between them. And of course, a special case is very important. The original sequence, let us take as Dn equals 1/4, which is a very famous one. Then the minimal parameter chain sequence are going to be half. Then they are going to be half. This implies that they are going to be less than or equal to half. So AN is going to be the single parameter chain sequence, or in other words, the corresponding GNs are uniquely determined by this relation. So this is the information we have here. So they are uniquely determined by this relation. Of course, a much particular situation is we take a Carathéodory function, which is given here, which is a well-known Carathéodory function for all sigma between 0 and 1. This maps the unit disk onto the, it maps for all z in the unit disk onto the right of plane. And of course, once we take the Schur algorithm, applying the Schur algorithm on this Carathéodory function, we can simply find the corresponding Schur parameters as gamma n's given by this. And we know that there is a relation between the Schur parameter and this Verbaliski coefficients. The corresponding Verbaliski coefficients are going to be this one. So from using this, we will be able to get, since we are getting the Verbaliski coefficient, we will find the corresponding minimal parameter sequence. And from that, we will find the complementary chain sequence and find the resultant equation. So delta n's are basically minus gamma n's. The moments are given by this equation. From that, we get the parameter sequences Kn, which is going to be the complementary chain sequence given here, and the constant sequence, which are going to give us 1/4. So if the original sequence is going to have delta n as a sequence, the other one is going to have 1/4 as the constant sequence. And precisely, this gives us the corresponding para-orthogonal polynomial in this particular way, which are given in this notation. And the orthogonal polynomial on the unit circle are precisely given by this relation. We're able to get all these things, and we summarize this result as whenever C of Z as a Carathéodory function whose positive Perron-Carathéodory fraction can give us this minimal parameter sequence, then using the complementary chain sequence idea, we will get for the complementary chain sequence, we get the corresponding function as retracing the Schur algorithm, we get the Carathéodory function as 1 over C of Z. So whenever C of Z is given, it is going to give us a particular chain sequence alpha n. So once we take the complementary chain sequence, it is going to give us retrace and give us the new Carathéodory function, which is 1 over C of Z. We are able to get these results. And not only that, we have some nice illustration for the hypergeometric case. So we are interested in constructing the hypergeometric case, for which we took a particular case of CNs and these DNs as the chain sequences. And from these DNs, we were able to get the minimal parameter sequence. Once we are getting the minimal parameter sequence, and we were able to get the maximal parameter sequence as well, and the corresponding probability measure for this was constructed in our work with Ranga and Cleonase. We were able to construct the corresponding non-trivial probability measure for this alpha n's and mu n's using the Wovenski coefficient theorem. And we were able to get that the para-orthogonal polynomials are precisely given in terms of the hypergeometric function given here. So what we have started is, we have started with a particular chain sequence, and with this chain sequence, we are able to get a particular, we are able to get orthogonal polynomials given in terms of Gaussian hypergeometric functions. And these Rn's we are given here are basically the para-orthogonal polynomials, which are associated with the Szegów polynomial or the orthogonal polynomial on the unit disk, which are also given in terms of this Gaussian hypergeometric polynomial in this particular relation, and their Verbaliski coefficients are given in this particular one. Once we have these relations, we are able to find the corresponding minimal parameter sequence and maximal parameter sequence, and we're able to get a lot of nice results in this direction. But one of the important things is that we know that the Gaussian hypergeometric function always satisfy a contiguous relation of this type. And once you take this contiguous relation and particular type of these contiguous relations, and if you apply this given orthogonal polynomial which you have considered here, this Gaussian hypergeometric type orthogonal polynomial, and replacing these particular terms with the given contiguous relation, we are able to find the nice three-term reconciliation for this Rn polynomials. So precisely this is how we are able to find the three-term reconciliation. And once we have the three-term reconciliation, we are able to study all the required results related to the orthogonal polynomials and their properties. And of course, these alpha n's which you have found here, these are basically the corresponding chain sequences we had in this situation here. And of course, under the Szegów polynomials, with these particular conditions, or the corresponding Szego polynomials are obtained with this particular condition, which is going to be positive and precisely given by this Verbaliski coefficient. And these are all true only when we take gamma equals beta plus conjugate of beta plus 1. And of course, we have done this with one contiguous relation. And we know that there are 15 contiguous relations given by Gauss. Using these 15 contiguous relations, we can find several relations. But we have observed that taking any such contiguous relation and proceeding by this, we can get several polynomials. But the beauty here, what we did is, from the corresponding conditions on these Verbaliski coefficients, whenever we take any one of these 15 contiguous relations, the Verbaliski coefficient condition, the Verbaliski theorem, or the Schur algorithm gives rise to the same orthogonal polynomial Rn, or its Pfaff transformation. So what happens is, all these 15 contiguous relations, even though in general they are supposed to give different orthogonal polynomials, the corresponding different polynomials, the corresponding orthogonal polynomials which are given by the Verbaliski coefficients are going to be the same orthogonal polynomial or its Pfaff transform one. Hence, the given orthogonal polynomial which you have considered here is unique by its procedure. Of course, we have, based on this, for given complementary chain sequence, we were able to do only this. So once we can change the complementary, instead of this complementary chain sequence, if we take some other perturbations, we'll be able to get different things. And another information we can do is, these particular polynomials which you have considered here, we take these polynomials and we know that this basically they satisfy a generating function of this particular type. And these are the orthogonal polynomials which you have considered here. For this orthogonal polynomial which you consider here, they are given by the generating function. We see that they satisfy some sort of the positivity condition. These positivity conditions are related to the positivity of trigonometric sums as well. And of course, once we take some particular values for these things, we were able to prove that they are satisfying some interesting relations related to the work given by Vettori's or Young's theorems on cosine and sine sums and their positivity relations. And of course, when we speak about these perturbations, there are other perturbations which we are interested. Of course, for k equals 1, we have already considered one particular situation. With other relations, we are able to get several other new type of results, and some of them are still open problem. And of course, the first one we have done in we have put it in archive. The other two cases are still open, and those who are interested can study on them as well. And these are the references we use. Basically, the work of Chihara is the book by for orthogonal polynomial, and of course, the Barry Simon's book also is much useful here. And the Deltsartke-Green para-orthogonal polynomial, where we have studied the Levinson's algorithm or the Schur algorithm we have studied. Basically, the Schur polynomials are given by the Jones and Neustadt in their work, and the quadrature formula of Roning's work was taken for our consideration. And the Szego polynomials for the hypergeometric function, the example was taken from the work of Ranga, and we have studied it here. And for the continuity fraction situations, the monograph of H.S. Wall was used. So these are the other references we have used in our presentations. And thank you. Professor Ahmed, you are muted, I suppose.
Yeah, thank you, Professor Swaminathan, for this nice lecture. And I'm really sorry we are running out of time.
I understand, and I thank the organizers for giving me such a nice time to talk. And of course, I know the time is short, so I was just hurrying up with my things.
Right.
If anybody has any questions, please mail me, contact me. I'll be able to talk to you.
Sure. So thank you for this. And so thank you very much. So our next speaker is Michael Scholzer. He is from University of Vienna. He is a professor at Department of Mathematics at University of Vienna. And Professor Scholzer also has held positions at Ohio State University and Northwestern University. And he is an specialist in the areas like special functions, Q series, enumerative and algebraic combinatorics, and many other related areas. And he has published more than 75 research papers, edited 3 books, and he has made some very fundamental contributions in the field of in the theory of multiple basic hypergeometric series and elliptic hypergeometric series. So it's my pleasure to have Professor Scholzer with us for this talk, and I'm thankful for having accepted our invitation for delivering a talk in this conference. So I welcome you to this session, and I'll request you to start your talk.
Okay, thank you very much. I don't have the permission to share my screen, so
yeah.
Okay, now I see.
Yeah.
Yes. Okay, can you see my screen?
Yeah, it is visible.
Okay, so thank you very much for the invitation. I'm very pleased to talk on Ramanujan's birthday and at this prestigious conference. So I would like to present work, joint work with Mian-Hong Zhou from Guangxi Normal University in China. And this will be on the infinite Borwein product raised to a positive real power. So I want to give you some background information, explain to you what I mean by infinite Borwein product, some motivation. Then I will present some asymptotic results without going into the proof, but I will just explain the ingredients used in the proof. And then I will pick up this particular case and I will explain you some arithmetic properties which follow, and these will concern the so-called cubic Borwein coefficients. So what do I mean by infinite Borwein product? It is this product, GP of Q. It's an infinite series. It's people familiar with Q series will recognize such series. So it's essentially can be well, 1 over this expression has a partition theoretic interpretation and would have positive coefficients. But this series has alternating coefficients, or at least it has positive and negative coefficients. And this product was considered by Borwein in the early 90s. So this is why I call it the Borwein product. So Peter Borwein considered this product, according to George Andrews. And we will consider real powers, positive real powers of this product, and consider the Q-series coefficients of that. So these will be denoted by Cp of delta of n. Yeah, so P is a prime. Later I will relax this condition, so P will be just some integer, but for the moment P should be a prime. And the nth coefficient of the delta of power of this product will be denoted as Cp to the power delta of n. Okay, and we will call these Borwein coefficients in this talk. And if we don't have any delta, or delta is just 1, we denote this as Cp of n. And this is what Andrews observed, so that these coefficients, they have a sign pattern. So Cp of n and Cp of n plus p, so it's periodic with period p. They have the same prime, these coefficients. They have the same sign, yeah. And one can write it in this form so that the product is greater or equal to 0. And in the same paper, Andrews studied other results, or actually ideas of Peter Borwein. He looked at the so-called Borwein conjectures raised by Peter Borwein in 1990. And they concerned periodic sign patterns of certain polynomials defined by finite products. So while this is an infinite product, and I call this the infinite Born product, and we'll raise it to an arbitrary power of delta, the Born conjectures, they concern certain finite products and with particular exponents, 1, 2, yeah, not necessarily real delta, arbitrary real delta. So this is the first Born conjecture. So this particular polynomial on the left-hand side, if you expand it in powers of q, every third coefficient is positive, and the others are all negative. So this can be written in this form. So because this is a polynomial, an of q, bn of q, and cn of q are also polynomials. And now in q to the third, so because we're picking every third coefficient, and these correspond to the residue classes of k to the of m. One looks at the coefficients of q to the m. Residue class is mod 3. Okay. The first Born conjecture also has a partition theoretic formulation, but I will not really need that here, but that was given by Judge Andrews as well. The second Born conjecture is essentially, you look at the same product as before, it's the first one, but now you square the left-hand side. And again, you have a sign pattern, plus, minus, minus, plus, minus, minus, and so on. Periodic sign pattern, period 3. And there's a third Born conjecture, so it's not about the third power, but that we will talk about later. The third Born conjecture considers a similar polynomial, but now with residue classes mod 5. So you take, instead of 3, you have 5 playing that role, and you have 4 products, so the fifth product is missing. Similarly here, the third product was missing. So you expand this in powers of q, and again, every fifth polynomial is now positive, the others are all negative. Okay, a lot of work has been done. And finally, Chen 1, almost 2 years ago, in January 2019, a PhD student at the University of Vienna, actually of a PhD student of Christian Krattenthaler, a colleague of mine, he settled the first Born conjecture using asymptotics. So this idea to use asymptotics was already laid out in George Andrews' paper. They have, Krattenthaler and Chen 1, together they have announced that they can use a modified method, which Chen 1 used to prove the first Born conjecture, now to prove also the second Born conjecture and other related conjectures. Maybe even the third conjecture. But there are certain bounds involved, and the bounds might be quite large. So it might still not be possible efficiently to prove the conjecture, but one can get very close to it. Chen 1 also made the following related discovery, which was somehow missed by Peter Borwein, it seems, or at least not stated explicitly, and also missed by Judge Andrews, that if you take the third power of this finite Borwein product related to mod 3, then you again have a sign pattern, plus, minus, minus. That's interesting. But this doesn't continue. So if you take the fourth power, you will not have this pattern anymore. And if you take real powers, arbitrary real powers, also not. But with the infinite product, things work nicely. So now I want to turn a little bit to Q-series notation. So a q sub n is this q shifted factorial, 1 minus a times 1 minus aq, and so on, n factors. If for infinite products we want to have q less than 1, an absolute value, and we conveniently write this product notation for shifted factorials. And one of the most important identities is Jacobi's triple product identity. Q series. So you have a bilateral series on the left-hand side and a product, three infinite products on the right-hand side, the Q, the Z, the Q over Z, with base Q sub infinity. And the n equals infinity case of the first one conjecture, what can be easily proved using Jacobi's triple product identity. This I just want to show you how this works. Of course, this is well known. Judge Andrews actually showed that these polynomials appearing in the first one conjecture have this series representations, but one cannot really see that they are positive, so that they're Q positive, because we have alternating signs. So we have -1 to the lambda. So we have infinite, formally infinite sums, but indeed, because of this binomial coefficients appearing in the summand of ANQ, BNQ, and CNQ, the sums are indeed finite. They are truncated from below and from above. And we're using Q binomial coefficients in these sums. So if you expand this out, certain powers of Q are the same, and they will contribute to non-negative coefficients in the end. But one does not see that immediately. But that's not the point here. I just want to now let n go to infinity, and you see that these binomial coefficients essentially drop out, and you get 1 over Q sub n, which is left. You can pull it out of the sum, and what is left you can evaluate by Jacobi triple product identity here, because you have Q to some quadratic power and some argument, and you can just identify what Q and what Z should be, and that is being done here. So if we let n go into infinity, we evaluate whether we have this 1 over Q sub infinity, some triple product, and but writing this Q sub infinity in base Q to the 9th, we have more Q shifted factorials in the denominator and the numerator, and everything is then clearly Q positive or Q non-negative. Okay, so for n going to infinity, it's very easy to prove this. So what we will now look at, not the finite product, but at the infinite product. But well, now we take different powers, not power 1, power 2, power 3, but power delta, with delta greater than 0. So this GP of Q, which I call the infinite Foreman product, now I take an arbitrary prime P. For prime P equals 3, we have this Foreman product now as an infinite product. And recall that the coefficients of that were denoted as Cp to the delta of n. Can you hear me? Okay. Then last year in September, I made the following conjecture, and this was dedicated to Dick Askey. So if one takes this G3 of Q, so this Foreman product with modulus 3, and raises it now to power delta, where delta is between, well, 9 minus square root of 73 half and 1, or between 2 and 3, then the coefficients appearing in the Q series expansion have the sign pattern plus minus minus. So for delta in other ranges greater than 0, we also have the sign pattern, but from a certain coefficient on. For large enough coefficients. But in this particular ranges, in the union of these two ranges, it seems that the sign pattern is already from n equals 0 on. So there's like a case where there's like a border, and I actually don't even understand why we have 9 minus square root of 73 half there, but okay. So you can, this can be checked numerically. Let's say you just expand this as a power series, the Taylor series expansion, and go up to order n and observe this simply. Yeah. So one way to attack this would be using asymptotics. One can do this for a particular delta, but it's difficult to make a proof which would be valid for all delta. So then new methods may be necessary. But I will show you some partial results. So the full conjecture is still open, but in joint work with Yin-Hong Zhao, we made an asymptotic expansion. It does not prove everything, but it proves something, and I will show you what we have so far. So for delta equals 1, the conjecture, of course, is known. So I just showed you the proof. It uses Jacobi-Kripal product identity. It's a well-known case. For delta equals 3, that's also interesting. We have a result for any prime p, not only for p equals 3. That will be done in the end. If I have time, I might need to skip that. And for other values of delta, we make an asymptotic approach. So there are two steps essentially. One step is to apply the Hardy-Ramanujan-Rademacher circle method to arrive at an asymptotic formula for the Bormann coefficients for any prime p. The formula will involve modified Bessel functions. In the next step, we specialize. So we take p equals 3, and we apply certain known monotonicity results for ratios of modified Bessel functions, together with some numerical estimates, to show that the conjecture holds. And now for a particular delta, within a certain numerical range of real numbers, and also when n is large enough. In our case, we have confirmed that the proof is for n greater or equal to 158. Okay. Of course, there are infinitely many cases if one varies delta. So it's not that, like in the Bormann case, that you have a finite number of cases to check in the end. So here you have countably infinitely many cases to check, uncountably many cases to check. Yeah. Okay, so I want to present the theorem we are using, but I just give you the ingredients, not the proof. So we want to study, well, we want to apply the Rademacher circle method. We take f of q, this is the generating function for partitions. This appears in this infinite Bormann product as quotients. With certain modular transformations have to be applied. And then we do contour integration. The Rademacher circle method gives rise to certain exponential sums involving these exponentials, where in the exponent you have so-called Dedekind sums. So this is just technical for those who are familiar with the circle method. They will recognize these ingredients. Otherwise, it just gives you a flavor of what is used. And we need also in the statement the modified Bessel function of the first kind, which has here positive coefficients. If z is, as far as z, and this is an entire function z. This comes out naturally. Okay. And here's the result. This is actually an exact formula for any m by the Hardy-Ramanujan-Rademacher circle method, or by Rademacher's perfected circle method of Hardy-Ramanujan. It gives a finite sum here with these exponential sums involved and the modified Bessel function as well. Delta in this version is between 0 and 24 over p minus 1. This can be strengthened, but when the expansion would look different. But this is the result we have for our partial results. And there's a certain error term involved here, which is bounded. It's O of 1. So it does not depend on capital N or on small n. Okay, but it depends on this delta and then P, of course. Okay, so this is just to give you a flavor of the result. Then we take P equals 3. Then I told you we use some estimates for these modified Bessel functions. And in the end, at least for delta within this range, between essentially 3 minus some epsilon, we have 2.9999 for just, but it can be closer to 3. And for some positive number, we started with 0.227. But again, if one has more computer power, one can go closer to 0 as well. We have the sign pattern. So we established that the coefficients have the same sign, and it's periodic with period 3. Okay, so this is a partial result, and now I'm not sure how much time do I have still. Can you kindly let me know?
Also, you can take 5 to 7 minutes.
Okay, so thank you very much. Now I want to concentrate on delta equals 3 case. So because there we have some quite exact results, not asymptotic results. So that's quite interesting. So similar to Chen-Wang's conjecture, where the third power of the finite War-1 product has also this nice arithmetic properties. You have a sign pattern plus minus minus. Now we look at the infinite product. Of course, for the finite product, you have Chen-Wang's conjecture, but now we take not modulus 3, but any prime p. So the roles of delta and p are interchanged essentially. And you probably recall Andrew's result for delta equals 1. So the infinite War-1 product for any prime p had this sign pattern. And now we have it for the third power of this infinite War-1 product. So now delta is not any real number, but it's really fixed to be 3. Yeah. It's not difficult to prove this. This is now done not asymptotically, but exact by elementary means, essentially. We look at a certain eta product raised to the third power and expand it as through dissections, expand it in terms of theta products and Lambert series. And here's what we use. We haven't seen this result in the literature, so it might, because the proof is elementary, it might be known, but we're thankful to references for this, but here it is. So k is now not a prime, but it can be a positive even integer or an odd integer. So we do a dissection in k, or actually, yeah, and then we actually have a bilateral sum and put two pieces together essentially. But anyway, so that's why we have k minus 1/2 in both cases. We also have the middle term here on the case of positive odd integer. Okay, but with the coefficient k here, which is divisible by k. That's one thing one can see. Okay, well, anyway, this is just, these are identities which are used, which are proved elementary, as I mentioned. One also needs the logarithmic derivative of the Jacobi theta function and then evaluate it at a certain point. The k equals 2 cases, k equals 3 cases of this proposition, so the two different cases, they actually reduce to prominent identities, Jacobi's sum of two squares theorem, and an addition formula for Forwards cubic data functions in disguise, of course. So one has to really, one has to do a little bit of work to see that one has these two identities. But if you're familiar with the, at least the squares theorem, sum of squares theorem of Jacobi, you maybe recognize these Lambert series appearing there. Okay. But we can now get, we can deduce vanished. So this theorem is, this proposition is used to prove this result. I'm not showing you now how it works, but I'm just again showing you the ingredients. Other consequences are vanishing conditions for the cubic Forward coefficients when k is an odd positive integer, because in this case I already mentioned this k is divisible. I mean, this is divisible by k, and this series can be expanded in positively. This not, because we have a plus here, because of this minus. So that's why we look at this case here, case odd. Okay, and this is one of the results we have. So the coefficients are congruent to 0, so they're divisible by k. In this, for these values, so if n times k plus k squared minus 1 over 8 for any n and any k. And here's another corollary. So there's a certain condition. So we count the number of recurrences of L mod k, for which these 12 plus 1, so the odd squares are congruent to 1 plus 8 h mod k. Looks a bit artificial, but it comes out naturally by comparing coefficients, essentially. So for those h's appearing there, for which there is no such L, so if the multiplicity here in this set is 0, then these coefficients vanish. One can just carry it out for k equals 3, 5, 7, 9 for any given k, and for instance, the 3n plus 2 for any n is 0. So C3, so for the mod 3 case, in the infinite Forward product to the power of 3, every third coefficient is 0, but with residue class congruent to 3 mod, congruent to 2 mod 3. And similar, if you look at k equals 5, again a prime, there are 2 residue classes where the coefficients are 0. And with 7, even 3, and with 9, there are 5 of those. So many coefficients actually are 0 and vanish. And we have a precise condition when this happens. So thank you very much for your attention. And yeah, if you have any questions, please let me know.
So thank you, Professor Scholzer. And I want to thank you for accepting our invitation and delivering this nice talk. And hope that next time in our meeting, you can come to India and deliver a talk in the conference.
Okay.
Thank you very much. Thank you.
You're welcome.
Thank you. So you can please stop this. Yeah, thank you very much. Our next speaker is Professor Bhargava from University of Mysore. And Professor Bhargava is one of the senior most Indian mathematician. And he is a specialist of number theory, special functions, Q series, Ramanujan mathematics, optimizations, applicable mathematics, and mathematics education. He has made some remarkable contributions during last 40 years in these areas of mathematics. and especially made some significant contributions in solving many mysteries surrounding Ramanujan's work. And his work on elliptic functions, Ramanujan's continued fractions, Q series, and theta functions are one of the most cited researches in the literature. And he has been the president of Indian Mathematical Society, and he was also the vice president of the Society for Spatial Functions and their applications. And he has been given many prestigious prizes for his contributions in mathematics. And I'll express my sincere thanks to Professor Bhargava for having accepted our invitations for delivering a talk in this conference. And I'll request you to please start your talk.
Thank you very much, Professor Amit, for your kind invitation. Nice words. I'll go to share screen.
Yeah.
Okay. Then I'll single click then go to share again. So, am I all right?
Yeah. Yes.
Continue.
Yeah, we can see your screen.
Okay, full screen.
Yeah.
Thank you very much.
Yeah, it is very well visible.
Friends, most of us are familiar with the monumental biography of Ramanujan, The Man Who Knew Infinity, published in 1991, a few years after Ramanujan's birth centenary. And the author is a professor of science writing at the Massachusetts Institute of Technology, Robert Canning. And this famous book has been translated into many languages, including many Indian languages. About 2 decades prior to this book was published another historical biography of Ramanujan, and it's a first of its kind. It's a 2-volume book by title Ramanujan Memorial Number. Volume 1 published in 1968 and Volume 2 published in 1967. I'm sorry, Volume 2 was published earlier, but for reasons, obvious reasons, I guess, the difficulties the editor and his team went through. And this is about the time of 80th year of Ramanujan's birth. And the publishers were a bunch of students, old boys of the high school, Mutiarpet High School, Number Friends Society, Old Boys Committee. That's the name of that bunch. And they were led by their teacher, P.K. Srinivasan, and he called himself the editor. That's a modest name one can attribute to him. It is actually an architect of those 2 volumes, and he struggled for it for decades. And he was born, Srinivasan, P.K. Srinivasan was born 4 years after Ramanujan's death, almost the time of Ramanujan. And he obtained his bachelor's degree in mathematics in 1947 and in teaching in 1948. So most of you know that 1947 was the year we Indians got independence. And Srinivasan obtained his master's degree in education while he was working 10 years later, in 1959. And all his degrees were from Madras University. Srinivasan started his teaching career in village schools right after his graduation in education. That's in the year 1940. He taught in a number of villages and villages around the town of Coimbatore. It's now called Kovai. Madras is now called Chennai, I guess. Kovai, I'm right. I guess I'm right. And having read about Ramanujan in his student days, he had a lifelong mission, in his own words, to spread the inspiration of Ramanujan's singular life of extraordinary creativity in mathematics in order to discover potential Ramanujans. So that mission entered his mind right after his graduation. And of course, it was about the time of Ramanujan himself, as I said. And news about Ramanujan and his accomplishment were fresh, especially among the population of India and around Tamil Nadu, the home state of Ramanujan. So, P.K. Srinivasan had read about all of Ramanujan during his student days in schools and colleges, and then he began his discovery of potential Ramanujans among the very village children he taught. So for this purpose, he made a platform, so a suitable platform, which he called Number Friend Society. That's in 1948. And that served as a suitable platform for children and even the general public of the villages, interested villagers and interested students, as well as his colleagues, to perform various academic activities. These academic activities included the exhibitions which the children could put up, and the discussions the children and the public could have about mathematics and mathematicians, and some exhibitions and even processions in villages. So that's the kind of initial actions that P.K. Srinivasan took in villages about popularizing Ramanujan. Well, many of us know Arvind Gupta, the Padma Shri Award by the government of India for his accomplishments. He's a renowned educationist and author and a fan of P.K. Srinivasan. He says in his book, Hands on Mathematics, a popular book internationally, he says about Srinivasan, as a one-man maths missionary, he did more than anyone else to imbue children with the love for this most beautiful subject, mathematics, the queen of all sciences. So that's the kind of a tribute that Padma Shri Arvind Gupta gives to Srinivasan for his initial work and work which he did later to popularize mathematics and Ramanujan in particular. After 4 years of teaching in villages around Coimbatore, Srinivasan returned to Madras and he was posted to Mutyalpet High School, and it was later upgraded as higher secondary school, and probably now it's a college. And he served that school for next 23 years in various capacities, which you will know later. In Madras, enrolled more members. He could enroll more members for his society. Madras was his hometown, state capital, as well as the place Ramanujan spent some crucial years before he left for England and after he returned to India from England. So it was a proper, Madras provided proper circumstances for Srinivasan to increase his activities, and by Ramanujan's 75th birthday in 1962, Srinivasan had done a great lot in acquiring Ramanujan materials. He had met Ramanujan's friends, wife, relatives, and contemporaries. And of course, he had no funds. He had to generate his own funds for all these purposes, for travel and all such things, which he did in those days. And he acquired letters, photographs, clippings, and all possible Ramanujan materials available with our friends and others, Ramanujan's friends and others. And he even went to offices where Ramanujan worked for a short period, especially Port Trust of India, where he worked as a clerk, a meager clerk, and also found some of his important mentors who helped him to get out of those situations. Taking advantage of Ramanujan's 75th birthday celebrations held in Madras, the sponsors were the state government itself and Madras University, and even Postal Department of India was involved in it. They brought out a special stamp in honor of Ramanujan. And taking advantage of this, Srinivasan arranged exhibitions and lectures by eminent persons and ensured active participation of large number of his students in these celebrations. So he and his students and other interested members of the society, of his society, were all over Madras. And the authorities of the state government, as well as the Vice Chancellor of Madras University and the public at large, were highly impressed by what Srinivasan was doing to the cause of Ramanujan's cause and the cause of Ramanujan's mathematics. So, encouraged by the appreciation he and his students received, he toyed with the idea of bringing out a biography of Ramanujan, which he called Ramanujan Memorial Number. And he also toyed with the idea of setting up a Ramanujan Museum. That is during 1962. He got that idea. Of course, he was partially equipped to do that. He had acquired Ramanujan materials like letters and photographs and other correspondences and some plaques and his slate and so on and so forth. But that was not enough for him to realize his dreams. So what he did was to set up a 7-member committee, which he called the Mutyalpet High School Number Friends Society Old Boys Committee, a long name. It consisted of some of students of Srinivasan, and later on, some of these went on to become famous mathematicians and statistics of our country. And with the help of these 7-member committee members and their friends and acquaintances, he could generate some funds and acquire more of Ramanujan's material. And the publication of the first of its kind 2-volume memorial number became a reality around Ramanujan's 80th birthday. So we worked for another 5 years to materialize that. Volume 1, I already gave the titles. So true to the titles, Volume 1 comprised original letters in photostats and reminiscences. And Volume 2 was devoted to mathematical contributions by eminent persons, and it is devoted to education and entertainment. So it took 5 years. In all, it took many decades from the date of from the date he from the day he went into villages, school teach as a village as a teacher to 19 to the 80th birthday of Rama. It took many decades of hard work for him and his students to do this. Realizing the museum turned out to be yet another challenge, of course, because he had to get a proper venue for that, a building he had to hire, and he had to put up all the exhibits that he had as Ramanujan materials, exhibits of Ramanujan materials, and so on and so forth. It involved much more funds, and he was also getting closer to his retirement. So in the year 1992, well after his retirement, thanks to our Academy, Chennai, and his resourceful old students and their associates, especially A.T. Bose, an educator, an entrepreneur and philanthropist, he could put up Ramanujan Museum in 1992. So we can't say he worked single-handedly, but he worked with the help of his students. His students and old students and current students came to his help and their acquaintances. So he became the first curator director of Ramanujan Museum in 1992, and a math education center he also set up. The education center served the purpose of holding periodic meetings, holding quizzes for school children, high school boys, and college boys. I think it's going on even now, such activities. And he served the center for almost all his life, the rest of his life. He died at the age of 81 in Madras after a year-long suffering from acute gastric disorders. He used to give, Srinivasan used to give lectures for interested public and publish his lecture handouts. And in one of the lecture handouts, probably it was his last one, he describes about the dedicated efforts he made until his official retirement and decades beyond, as well as the ordeals he faced while spreading his mission, bringing out Memorial Number and his other books, and establishing the museum. And he also served as Fulbright exchange teacher in the United States of America after his retirement. And he worked for the Nigerian government. And he had also served the National Council for Education, Research and Training of Government of India. And he also wrote many books for children of pedagogic importance. And the best description, once again, the best tribute to Srinivasan, crystallizing all his efforts, all his life, is once again given by Padma Shri Arvind Gupta. He says, P.K. Srinivasan was the greatest proponent in India of learning math through activities. Srinivasan breathed mathematics, he dreamt mathematics. More than anything else, he rubbed this infectious enthusiasm on everyone he crossed his path. He cried, he wept, he pleaded with one and all that mathematics was all around them. And when no one listened, he wrote articles in newspaper, local newspaper, the Hindu. And he wrote about 60 articles that have become classics, the words of Arvind Gupta. And now these articles have been collated and published as a book. by title Resource Material for Mathematics Club Activities by National Council for Education, Research and Training. Now, I can briefly let you know about the contents of these two volumes. Ramanujan, two volumes in Ramanujan Memorial Number. So, volume 1 comprises original letters in photostats, and these constitute a primary and most authentic source, and reminiscences, the impressions that Ramanujan's friends and contemporaries and others who came across Ramanujan, their impressions. These reminiscences forming the secondary source. Most of them are published for the first time. The letters appear in two sections. Thus he wrote, and what they did and said. Of course, the obvious meaning. Thus he wrote consists of the letters he wrote to his friends and to other famous people seeking help to publish what he did, and also seeking help to eke out his livelihood, and what kind of reply he received from them. So these letters reveal not only the mind of Ramanujan, but also the minds of those of his followers who had a difficult time with his work. And followers, in the sense that the recipients of those letters who tried to follow what Ramanujan wrote, those letters, like Hardy, for instance, or other British mathematicians and Indians who took some time to find out what kind of mathematics he was writing. Ramanujan sent samples of whatever he did, large samples to people whom he wrote, especially to Hardy. The letters have been arranged not on a mere chronological basis, but bunches centering around recipients and senders. So this speaks of the efforts Srinivasan and his old boys took in doing all this manually. It was all manual in those days. No computer existed. Most of the titles and paragraph headings have been supplied as a part of editorial work. So that shows how much pain Srinivasan took in going through this in detail, the letters, and supplying proper headings. And the section thus he wrote contains excerpts of 4 of Ramanujan's letters to Hardy, 13 letters, 4 each to his friends, Krishna Rao and Subramania, and 1 each to Madras Port Trust and S. Narayana. Madras Port Trust is where he worked before sailing to England. And Narayana was a manager at the Madras Port Trust who helped him, who he and the director also exempted Ramanujan from regular clerical work. In fact, they helped him with the stationery and time and money to do his own thing while he was enrolled as a clerk in Madras Port Trust. So he wrote letters to his parents, of course, in Tamil, in his language, and he also wrote letters to registrar, many letters to registrar perhaps, and one of the letters has been included by Srinivasan. And what they did and said, that is the reply or other kinds of messages he received. That section contains a total of 16 letters. 2 are about Ramanujan. The names that appear, the names of the people, a gentleman, or some of them are Middlemast, Griffith Spring. Francis Spring was the head of the Port Trust of India at that time. Born Francis Graham Hill Griffith, Walker, Dewsbury, Register, Hardy, of course, his mentor, Neville, who took pains to personally meet Ramanujan and convince him to go to England and join his mentor Hardy. And then there are a lot of others involved in and the reminiscences section contains over 35 contributions of eminent academicians, administrators, Ramanujan's friends, his relatives, and his contemporaries. There's 35 plates and other usual things like appendixes, index, acknowledgement, and so on. Volume 2 is mathematical. It's devoted to mathematical contributions, devoted to education and entertainment. And it is devoted to mainly popularizing mathematics. And is of interest to students as well as teachers. Provides a lot of background materials. It has 3 sections. Volume 2 has 3 sections entitled Excursions into Numberland, Through the Mathematician's Eyes, and Catch the Men. And Srinivasan took a lot of pains to approach a variety of prominent people and less prominent people, working teachers, students, and famous people and less famous people, teachers, public, etc., etc. And of course, helped by his old students. And he ensured realization of the purpose of the volume so that it can cover various different aspects of what he intended the volume to cover. It bears an all-India character in the sense, apart from the famous people at that time, G.N. Watson and J.B.S. Haldane, he chose budding school, college, and university teachers and researchers of the day, and even amateurs, to write articles for that volume. And I've listed the names of the people involved, and some of them, like J.N. Kapoor and S.S. Pillai, you may recognize, and Hansraj Gupta and Jyotirlinga. A number of authors of the articles were involved, a number of them. Excursion into Numberland includes elementary articles on such topics, familiar topics. We are many of us are familiar with these topics: magic squares, number patterns, algebraic identities, irrational numbers, factorizations, representation of number as sums of powers, nested radicals, the taxi cab number 1729. For the latest development and relevance of this taxi cab number, where it fits in and what are the ramifications around, you can read Ken Ono's articles and collaborate with the students. Triangles, circles, prime numbers, etc. I mean, these titles tell us that the articles could be of nature of entertainment in nature, and also very have the direction of popularizing mathematics among school children as well as others, which was the motivation for him. And the other section, through the mathematician's eye, so consists of applications of mathematics, a common South Indian game we all play here, or some kind of modest version of chess, some aspects of modern mathematics, unsolved problems in Hindu geometry, written in Tamil, articles written in Tamil, and some results of Ramanujan. And Catch the Men concerns articles on education at all levels, from kindergarten to university. And I've given a list of and their authors. And Hansraj Gupta and J.B.S. Holden are famous people. And the volume ends with an article on Ramanujan, which is one of the articles, one of the institutions recently founded at that time. And to end with, I've given a number of I don't know what this means. Please move the window away from the shared application. Okay. So I've given references. Gupta's book Hands on Mathematics, published in 2005 after Srinivasan passed away, and P.K. Srinivasan's biography of Ramanujan, the Ramanujan Memorial Number, the 2 volumes, and then his books by title Number Fun with Calendar, Romping Numberland, his innovative and the talk given by Srinivasan as a curator, public, and then his resource material published by NCERT in 2015, quite a recent one. So, that's about what I wanted to say. I once again thank Professor Ali for the opportunity he gave me to share some of my thoughts. I thought I should make Srinivasan famous because I think he's one of the precursors of Ramanujan's, among Ramanujan's biographers, and of course it's one of the earliest biographies to be written, biographies of the kind where, of course, he could not interlace mathematics with Ramanujan's biography. He separated. That's the best he could do at that time, being a high school teacher. That's about it. Thank you, sir. Thank you all for listening.
Yeah. Thank you, Professor Bhargav. And there is one very relevant question from one of the participants, Gaurav Bhatnagar.
This is
that what are the efforts that have been made to publicize this work, to bring such books and other things in public?
Yeah, it's an unfortunate thing. In fact, this is based on my contribution to Encyclopedia of Mathematics, which Professor Bruce requested me to write. And at that time, I couldn't find these books easily in India. I could borrow one of them from local library, Regional College of Education, but for a limited time. And when Bruce visited me, he told that he possesses these 2 volumes, and he sent me on his return. So, and I even approached Mutyalpet High School for these books, but they did not have a proper answer. So I think these books, these 2 volumes should be reprinted and sold for a very small sum of money.
So let's hope that some initiatives will be taken in a very near future to make.
Someone probably should write to either Mutyalpet High School or NCERT or to reprint these books. I have 2. I have the books which are burnt spared.
Okay.
I think we should write to maybe our societies, the Society for Special Functions, may request NCERT to publish these books, republish these books.
Yeah, we can take some initiative.
Print them, because even today it stands on its own. It's very valuable.
Yeah.
In fact, wherever I go, I recommend the question I am usually asked in schools and colleges and even universities when I give a talk about Ramanujan's mathematics. The usual question they ask is, how is it? How can any even children or ordinary public appreciate Ramanujan? Uh, there are simple, trivial things, trivial mathematics published all over and made popular. Does that make Ramanujan popular? And so on and so forth. Then I say, please read biographies, starting with P.K. Srinivasan's, and then the articles and biographies, books written by Bruce Berndt and Andrews and Bruce Berndt. They have written a lot of, and Bruce Berndt himself has a number of books in this style, letters and reminiscences and other books. With those titles, Bruce Berndt has written a couple of 2 or 3 books of that type, and of course Canigal's books. So I ask everyone to read Ramanujan's biographies first and pick up whatever they can. That everyone can find something or the other, especially when they go through P.K. Srinivasan's book. It's very simply written and accessible to ordinary people for reading, lay public. So that's the recommendation I make. Most people should read biographies about Ramanujan and pick up whatever they can, whatever mathematics they can. There's a lot of P.K. Srinivasan's books. Canigal's book, of course, has much more. It is much more mathematics interlaced Ramanujan's mathematics. So one should read those books, and we should have these 2 books reprinted and sold at a sum affordable to everybody. That's my answer. I don't know whether I answered the question.
So thank you, Professor Bhargava, for such an informative lecture, and especially bringing the work of Srinivasa to the notice of the audience. And I hope that in near future, there will be some initiatives to popularize such literatures, and they will come to the and the common public even will have an access to such kind of literature. So there was there are one question from the audience that will these lectures will be on YouTube? The answer is yes. We will share the YouTube links of all these lectures immediately after the conference. Another important information for some participants, there were some queries about the participation certificates. In the next session, we will share one link of certificate issue request form. And if you are willing to get a participation certificate, you can fill that form online. We will mail you the certificates on 24th. So we are coming to an end of the session. Our session 3 will start at 2:30 Indian Standard Time, and there are 3 speakers in the session. The speakers are Tom Kurwinder from University of Amsterdam, Atul Dixit from Indian Institute of Technology, Roorkee, and Dimitri Kar from Holland Technological Institute, Israel. So I hope you will all join us again in session 3 at 2:30. So thank you very much for joining us, and thank you very much. We come to the end of this meeting. Thank you.